let us estimate the joint load vector, because if you look at the figure, the structure does not have any member loading, it has only one load in the joint. So, directly I can write the joint load vector, because there are no fixed end moments generated by the loads on the member. So, one carefully can observe that this 10 kilonewton load is applied along with the degree of freedom, which is 3, remaining all joint loads are practically 0. So, with this logic, the joint load vector can be entered as 0 0 plus 10 okay. So, there are 12 1 2 3 6 9 values, is it not? There is a 9 degree of freedom we have total 9 degrees of freedom, is it not? So, we have 9, the vector is 9 by 1. So, one can make a submatrix of this. So, this is JL unrestrained and this is JL restrained. Okay. Why unrestrained? There are 3 unrestrained degrees of freedom for this problem. There are 3 green unrestrained degrees of freedom. Therefore, I partition this matrix at 3, this means JLU. So, JLU is actually 0 0 plus 10. In fact, I can call this as JLU bar, is it not? Because these degrees of freedom are related to the reference axis system xy. Okay. I get the JL bar. Once I get that, I can now find the total stiffness matrix. First, let me find K bar of each member as T transpose of the ith member with K of the ith member with T of the ith member. So, now I can do this for K A B, which will be T transpose of A B, K of A B and T of A B. Then I do this for B C, which will be T transpose of B C, K of B C and then T of B C. Now, K A B will have labels K A B, K bar A B will have now labels. We already identify these labels 719283, is it not? So, 719283, these are global labels. So, 719283 and 3, these are global labels. Similarly, I can also find for KBC bar, which will again be a 6 by 6, the labels will be 1, 4, 2, 5, 3, 6, 1, 4, 2, 5, 3, 6. So, what I do? I assemble this matrix and get K total, I get K bar total, which will be a 9 by 9 matrix, which will contain a partition submatrices. This will be K U U, this is K U R, this is K R U, this is K R R, all will be bars because this is K bar, all will be with reference to the reference axis xy system now. K U U will be of size 3 by 3, I plug out K U U and K U U bar for this structure. can be worked out from the program, which we get this as E into 10 power minus 4. Before that, let us write down the values of, let us write down for simplicity, write down the values of k bar a b, which is E into 10 power minus 4, 14, 7, 2, minus 2, minus 4, 4, 7, 14, 2, minus 2, minus 4, 4, 2, 2, 215, minus 215, 106, minus 106, minus 2, minus 2, minus 215, 215, minus 106, 106, minus 4, minus 4, 106, minus 106, 55, minus 55, 4, 4, minus 106, 106, minus 55, 55. The labels will be 7, 1, 9, 2, 8, 3, 7, 1, 9, 2, 8, 3. This for k a b. Let us do it for k bar b c, which will be E 10 power minus 4, 16, 8, 6, minus 6, 0, 0, 8, 16, 6, minus 6, 0, 0, 6, 6, 3, minus 3, 0, 0, minus 6, minus 6, minus 3, 3, 0, 0, 300 and minus 300. The labels will be 1, 4, 2, 5, 3, 6, 1, 4, 2, 5, 3, 6. Okay. Now, assemble this matrix, get k total, then plug out k u u, and we get k u u, k unrestrained bar, which is 3 by 3 matrix, which will be equal to E into 10 power minus 4, 30, 4, 4, 4, 218, 106, 4, 106, 355, and the degrees of freedom would be 1, 2 and 3, which are unrestrained as the degrees of freedom for the given problem. Let us try to find k u u inverse of this problem, which will be 1 by E times of 330.863 minus 4.561 minus 2.631 53.769 . 32.980. Now, I do the operation of delta u bar, which will be k u bar inverse multiplied by j l u. Now, I have both of them. Okay. So, I get delta u bar as 1 by E minus 26.307 minus 160.545 and 329.804. Now, I can interpret delta bar A B as A B has 6 degrees of freedom. Okay. So, the values will be 0, minus 26.307, 0, minus 160.545, 0, 329.804. Delta bar B C will be is 1 by E of minus 26.307, 0, minus 160.545, 0, 329.804 and 0. Okay. Now, I want to find m bar, that is end moment and reactions of the member A B. In simple terms, I can use, if you want to find m bar of any ith member, I should say k bar of the ith member and delta bar of the ith member plus fixed end moments of the ith member, is it not? So, by this logic I can now find m bar A B, which will be, look at the degrees of freedom of A B, 719283. Okay. 719283. So, 7 rotation, 1 rotation. Okay. 9 and 2 are vertical reactions, 8 and 3 are horizontal reactions. Keeping that in mind, I can say now this is m bar 7, m bar 1 rotations, that is end moments, then vertical reactions, that is along y, then horizontal reactions along x at different levels, is it not, which is computed as 0.1572, 0.1384, minus 0.0639, 0.0639, minus 0.1059, 0.1059. This is for m A B. Let us do it for m bar B C, which will be, look at the labels of m bar B C. M bar B C has 1, 4, 2, 5, 3, 6. So, 1 and 2 are 1 and 4 are rotations, that is end moments, 2 and 5 are vertical reactions, 3 and 6 are horizontal reactions. Keeping that in mind, I can now write m bar 1, m bar 4, v bar 2, v bar 5, h bar 3 and h bar 6, is it not? So, which will be actually equal to minus 0.1384 minus 0.1174 minus 0639 plus 0639, 9.8941 minus 9.8941. Let us see the computer program how this works. So, this is the problem. There are 2 members in the problem, is it not? Let us use the green color. There are 2 members in the problem. I values are given as per the input, length of the members are given, area of cross section is given in square meters, theta is computed for each member. So, we need Cx Cy to calculate. Okay. So, that has been done here Cx Cy. Okay. There are 3 unrestrained degrees and 6 restrained degrees. The labels of unrestrained are 1 to 3 and labels of restrained are 4 to 9 as you see here. So, then we have the local member labels, the global member labels for 1 7 1 9 2 8 3, which is as same as this. See here 7 1 9 2 8 3, which is same as this. You can see here 7 1 9 2 8 3, similarly 1 4 2 5 3 6. Okay. Then obtain the transformation matrix for member 1 and member 2. Okay. Once this is completed, find the fixed end moments in this problem, they are 0. Find the rotational coefficients and the axial stiffness coefficient, we got the values. Once this is completed, obtain the stiffness matrix for each member. So, obtain K I local. Okay. So, print the local stiffness matrix, then find the transformation matrix and transpose matrix and obtain K global. So, now here you get K bar of I, which is nothing but K bar of I is T transpose K T of I, is it not? So, T transpose K T of I. Okay, we got K bar I of each member. Once I get that, we compute the FEM bar and find the stiffness matrix of the total structure, plug out unrestrained stiffness matrix and get the inverse. That is, we got K U U bar and we got K U U bar inverse. Once I get that, I create the load vector, create the joint load vector, plug out the unrestrained joint load vector, then I find the unrestrained displacement, okay, which will be unrestrained displacement in global degree will be K bar inverse U U inverse J L U. Okay, we got this. Once I obtain, I can find M bar of ith member as K bar of the ith member with delta bar of the ith member plus FEM bar of the ith member, which is the equation here. Look at the results. So, this is my member 1, this is my stiffness matrix local of the member 1, this is my transformation matrix of the member 1, this is transpose of the matrix, this is K bar, that is K global of member 1. Similarly, we get local matrix for member 2, transformation matrix. So, there is a multiplier here E, okay. There is a multiplier here E, there is a multiplier here E, again there is a multiplier here in K bar E. So, this is actually K bar A B and this is actually K bar B C. Once I have this, I assemble this and get the total stiffness matrix, which is 9 by 9, which is K bar total, where E is constant out. From this I plug out only the submatrix, which is U U, okay, which is 3 by 3. So, I plug out only this matrix and write this as K U U bar with E outside, is it not? Then I invert this matrix, I get K bar U U inverse with 1 by E out. Then I get the joint load vector, I partition this, I get J L U, okay, bar. Then I find del U, which is nothing but del bar U with K U U bar inverse of J L bar U. Okay, I get this. which will be 1 by E times of this. Then we find del bar of the member AB, then we find m bar of the member AB. Similarly, del bar of the member BC and m bar of the member BC. Let us plot these results and show how do they match. Okay. So, let us show these results. This is my original structural system. Okay. So, you know this is my m bar of member 1. The degrees of freedom of the structure, if you remember, I am just marking them again. Okay. This was theta 1, delta 2, delta 3, okay, and theta 4, delta 5, delta 6, theta 7, delta 8 and delta 9. So, for the member 1 the labels could be, you know, the labels are 7, 1, 9, 2, 8, 3 rotations, then along y and along x. Similarly, for the member BC will be 1, 4, 2, 5, 3, 6, correct, 1, 4, 2, 5, 3, 6. Let us now interpret the results. 0.1572, let me write down the values. This is positive, so anti-clockwise 0.1572, this plus again, so 0.1384, okay. Then 9 is here, this is minus, so downward 0.0639, then 2 which is plus positive 0.0639, then 8 is minus. So, this way which is 0.1059, okay, and 3 which is positive. So, let us say 0.1059, that is a E multiplier in all these cases, E is constant. Okay. This for member 1, let us do it for member 2. So, for member 2 the labels are 1, so let us say 1 minus, so it is going to be clockwise which is 0.1384, okay, and 2 is also negative, so clockwise 0.1174, then 2 is negative, so downward 0.0639, and 5 is positive, so upward 0.0639, okay. Then the degree of freedom 3 is positive, so 9.8941, and this is negative, which is 9.8941. So, friends, if you look at this problem was applied to a load of 10 kilonewton here, which actually amounts to 9.841 plus 10, it is exactly matching. Okay. That is how the problem is solved. So, it is very interesting. Friends, in this lecture we understood the computer program for solving a non-orthogonal structure. We have marked the labels and degrees of freedom, unrestrained, restrained, followed the exact procedure what we discussed in the derivation, and did the coding exactly on the same line and got the answers which is being solved for this problem. I hope you will understand and practice this particular problem again with the coding given on the screen, and you will obtain the same set of results. Thank you very much.